That was my ultimate t-shirt. Okay, so the quiz was tough. Somebody asked what the average was. I didn't actually compute the average, but a number of people got 100%. But then, in 95. But then there were a lot of people who got lower scores. And I think the questions were hard, but they were actually accurate if you read them closely. But the main thing is, I don't think this should be too discouraging for you. And then I want to make some observations. For one thing, this was like a big, sharp turn in the course when we got to chapter 7. I kept telling you guys it's coming, but nobody really believed me. Oh, it's not. Hello. Oh, that's better. All right. So I kept telling you it was coming, and it was coming. The good news is there's only one more sharp turn in the course left. So that was the big one. Chapter 7 was a big sharp turn because it involved putting together these ideas that are actually they're really simple once you understand them, but before you understand them, they're really not simple. But I really believe everybody in this class has the ability to figure out how these things fit together. Sum of squares and PRE and F to some degree. I'm not going to expect you to become mathematicians or anything like that. So, and chapter 8, which you just finished, I don't know how many you recognize that chapter 8 really was exactly like chapter 7. How many people sort of had that sense? Yeah, I mean, chapter 8, and we're going to spend this week talking about chapter 8, but also chapter 7. So I think that you're going to get these concepts down. And then there is one more sharp turn in the course, and that, of course, is chapters 9 and 10. And if you start at chapter 9, it's usually one of the hardest concepts. But again, you're going to have a couple of weeks to put it together. So I don't want you to be discouraged. On the other hand, I have to say, after we set up all these study halls, very few people are going to study hall. So if you're getting, A's, then I don't care if you go to study hall. But if you're struggling and your grades are lower, that's something you can do, because the people who are going to study hall are not on the list of the people who are really struggling to the greatest degree. Those people are getting something out of that. If you can't make any of the study halls, you can feel free to email me, and we'll try to set up another time. Adam off last week. So I really can't stress enough how just talking about these ideas is going to be really important. And I know it's hard to get you to talk in class, but honestly, the best way to learn this stuff is to say, wait, that doesn't make sense. And if you're too shy to say that, then we can't stop. And believe me, if it doesn't make sense to you, there's a lot of people that it doesn't make sense. So anyway, I really encourage you to get more help, because there is a lot of help available on going over these concepts. Just go to the study halls and talk about the ideas. You also can go and see your quizzes and see exactly what you got wrong. All the TAs have the quizzes, and I have the quizzes, so you can come to my office hours or go to any of the study halls, or if none of those times work, email any of us, and we'll be happy to go over the quiz with you. But again, I want you to understand why your answers were wrong, but don't think you can just memorize the answers to the quiz question. That's not enough. So there's other things you can do to deepen your understanding. So does anybody have any questions? Is anybody feeling a little discouraged about the quiz grades? If you are, that's fine. I understand it. I also have seen, by talking to people in my office hours and talking about the study halls, there are people who are starting to figure out how everything goes together. So you can do that too if you're someone who's not quite there yet. It's going to be fine. And the way the grading works in this course, I know you didn't read the syllabus, because students never read the syllabus, but we actually offer two different grading schemes at the end of the course. One heavily emphasizes the final exam. So you can, and I did that on purpose because it takes people different amounts of time to put this together. So if you kind of don't do that well on all the quizzes, but suddenly it all starts to come together and you do well in the final exam, you can do well in the course. I personally, it's sort of arbitrary that a course is 10 weeks. Sometimes it takes longer than that to understand things, sometimes shorter. But anyway, arbitrarily, that's sort of what we're stuck with, is exactly 10 weeks. But anyway, there's a lot of options, and I don't want you to get discouraged. And I do want you to go get help. And I also think when you're doing the online materials, and I've looked at some of the things that people are writing in the online materials. First of all, the open response answers for quiz 3 I thought were great. I think when you guys have the opportunity to put stuff in your own words, you're really starting to be able to do that, and that's great. On the final exam, it'll be pretty similar to a quiz, but it'll be quite a bit longer, but we'll also have more opportunities for open response. Maybe a slightly higher percentage on the final than we had in the other quizzes. So bringing me to the online materials, many of you are working really hard when you're going through the online materials and writing things and continuing to do that, even though you have the suspicion no one reads what you're writing. And even though to a large degree that's true. But we've read some of what I've gone through and read things, and I do know there's a range. Some people type, they may have it kind of wrong, but you can see the ideas are coming together and they're putting words to paper. You can learn a lot that way. Other people are typing JK, 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 thinking, wow, I just got away with a lot. Actually, you didn't get away with anything because you didn't learn anything by doing that. So, and ultimately, I actually don't care how you learn this stuff, but I will point out that some of the people who go JK, JK, JK are people who got pretty low scores on the quizzes. So, just letting you know, there might be a pattern here. It's not a perfect model, right? There's a lot of unexplained variation, but anyway. So for today and Thursday, I'm really going to focus more on consolidating what you know around sum of squares and PRE and F, applying that to regression models and trying to help you get that into your kind of DNA so that it comes naturally to think that way. We'll also try to spend a little extra time on F, which is probably confusing to you, but F is something that we're going to end up focusing on more the last week of the class. So we'll get started on it. I'm not too worried if you don't understand it in a very deep way. And correlation, we'll spend a little bit of time on correlation. And people I noticed had a lot of questions about what's the difference between a standardized and unstandardized distribution. So hopefully we can get to that on Thursday. But guess what? If we don't, that's what study hall's for. That's what office hours are for. And gosh, the rest of your life too, because we're only scratching the surface in terms of statistical modeling. There's so much more to learn. So I thought I would start by going over just the top most missed questions on the quiz. And I'm mainly doing this just so that you know that that I care. And just give you a sense. I think a lot of you probably, most time when people got the wrong answer, they didn't do a random answer. They got the one that was designed carefully to be like the foil, like G really loves to make foils that are hard to figure out. So I don't think you're totally off, but there are a few things that I think it's worth discussing. So first of all, if you use the distribution of weight gain, remember this is fat mice 18 data frame. If you use the distribution as a probability model, what's the likelihood of a mouse in a future study gaining more than 15 grams of weight? So the most common wrong answer to this was 0.025. And I think it's because you heard probability model and you thought, oh, I'm going to lay a normal distribution on top of that. But that's not what the question's asking you to do. It's asking you to use the data as a probability model. So it's just going to say, okay, whatever the probability, let's see, there's one mouse who got more than 15, and there were 18 mice in the data frame. So 1 over 18 is going to be our probability estimate if we're using the data as a probability model. Yes? Here, use this.
So I thought that initially when I looked at this, but then I read how would you use it to determine anything for a future study? And then I was wondering, say if this model had 20, that's a different percentage than 1 over 18. So how could you use it?
Right, yeah. So that's really a good point. The key is when you use it as a probability model, you're saying, all right, we're going to assume whatever the probability is here, or the proportion, is going to be our probability. Now, your point is really good. Is that a very good model? Probably not a really good model, because it's only based on 18 mice. If you had 20 mice, you never know what would have happened, and the probabilities all would have changed around quite a bit. So, on the other hand, if you had a sample of 10,000, this is probably a better model than you would get by overlaying a normal distribution, because 10,000 is a lot, and the distribution may not be perfectly normal. It may have a longer tail on one side, and you may get better probabilities from that. So the key is, what does it mean to use data as a probability? And it means, okay, we don't know. Remember, this is our sample. We're trying to find out about the data generating process, the population. We don't know about the population, but we're going to use this as a probability model. Remember, our models are not supposed to be, they're not good. They're just better than nothing. Remember? It's a theme here. Yes?
I'm confused why 0.025 is wrong.
0.025 is wrong because if you divide, because the right answer is 1 over 18. There's 18 mice. There's 1 who scored above 15. So the proportion who scored above 15, it's about 5%, I think, something like that. 1 over 18, a little more than 5%. So it just happens that 0.025 is the wrong answer if you use this data as a probability model. Okay, this is the supernova table. And you guys, you are going to need to get really fluent at reading supernova tables, but they're not hard to read. So above is the supernova table for light model, which uses light to explain variation in weight gain 4. What does the PRE of 0.60 mean? So when you think about PRE, before you even read the options, how do you calculate PRE? What do you divide by what? Who's got it? Just yell it out. SS model divided by SS total, okay? So SS total is all the variation that's there to be explained. It's what's left in the empty model. And we take the model and divide it by that, and we get a proportion of error that's been reduced. Or another way to look at it is the proportion of the error that's been explained by other variables. So, so the first one is wrong, has nothing to do with a 60% chance. The second one is actually the correct answer. 0.6 of the empty model's leftover sum of squares is explained by the light groups. The last option is the most common wrong answer people gave. 0.6 of the complex model's leftover sum of squares. But the complex model is the light model. And its leftover sum of squares is sum of squares error. Okay? Above is the supernova table for light model, blah, blah, blah. Y is the degrees of freedom for model equal to 1. And the answer is the light model uses up a degree of freedom by estimating one more parameter, b sub 1, than the empty model. Okay, the empty model has just b sub 0, and that doesn't go in the denominator. So that's the degree of freedom we lose when we take n minus 1 to estimate error. But way we get that 1 as a degree of freedom is the one parameter we're estimating beyond the empty model. And that's the B1. Now, the most common wrong answer to this is not a good wrong answer. It's a bad wrong answer. It's the second one, which is x sub I, or x sub I1. So x sub I is never a parameter. A parameter is something that cuts across the whole sample, and we estimate that parameter in the population. It's not something that varies from individual to individual. So it's the amount that we're going to multiply by 1 to get the increment for group 2. So that's multiple amount. That's called the parameter, and it's always the same. X sub I can vary across different individual mice. So so that's the answer to that. If anything has a sub I, it's not a parameter, because that means it must be about an individual. And a parameter is about the population. It's not about individuals. So sub I means it's something that varies among individuals in our sample, or individual rows in our sample. Do these results show that light treatment causes mice to eat more? Yeah, well, this is a question about causality, and a lot of people got this wrong, and I think I know why you got it wrong, because this was a random assignment study, and you all probably thought, well, I mean, a lot got it right too, don't get me wrong, but a lot of people probably thought, oh, it's random assignment, therefore we can assume, we could infer causality. But what are we really looking at? It's not, it's the light that caused, that we can say caused the gain in weight. But if you say no, because, yes, because the experimental design where mice were randomly assigned to 2 different treatments, that doesn't show that they ate more. So the real key to this question is, do these results that show that the mice ate more? No. These results, we didn't feed them more, and they didn't eat more, they just had different light conditions. So we make the assumption, and this is something that we're really good at, is filling in the causal chain. So we're going, oh, the light, they gained weight. Oh, they must have eaten more. And because it was an experiment, random assignment, it must be causal. No, we didn't show that. So we don't, the correct answer is no, because even though we know the light caused them to gain more weight, we don't know it's because they ate more. Yes?
What makes the last option a bad option?
Ah, that's a great question. What makes the last option a bad option? Because random assignment does take care of pre-existing differences. There are always pre-existing differences across your samples, but because it's random, you can assume that whatever differences there are that might pull one group up are going to also pull the other group up and down, and they're going to counterbalance each other. That's the whole idea. It's the same idea as when you add all the errors up, they balance each other out to get the mean. It's the same idea. So random assignment is designed to take care of pre-existing differences.
But in the beginning, it didn't explicitly say that it was random assignment, so should we have that? Should we have just assumed?
In fact, someone asked me during the quiz, and I said, just go with what it says.
It didn't say random
It doesn't.
assignment?
It just says that they track the weight gain, and that they put them in different, but it doesn't say that they randomly.
Oh,
I think both the last 2 are false.
wow. Didn't say that?
Because I was the one that asked him, and that's why I didn't.
All right. Well, I'm going to go back and review that. Unless you just want to trust Adam. I want to review it.
I was just gonna say, yeah, I mean, I specifically looked for like
Random
the words
assigned.
randomly assigned, and they were not in the prompt, so I assumed it was.
All right.
Yeah, it really does.
All right. Well, if it doesn't say that, I'm going to accept it. Let's see. If it's not randomly assigned, I guess I would accept the last 2 answers if it doesn't say random assignment. Now I'm embarrassed. All right. But that doesn't mean you shouldn't take the point. The point is, it's random assignment, it takes care of individual, like pre-existing differences between groups. Those differences should balance each other out because it's random. And just because you manipulated a particular variable, don't assume anything else is accounting for that difference except for what you actually manipulated. So you don't want to assume it's even. All right. Remind me, I'll look at that later. All right. The last one, I think. Above is the supernova table for light model, which uses light to explain variation in awakening. 4, why does the table show a smaller sum of squares error than sum of squares total? Well, first of all, we all know it's always going to be a lower sum of squares error than sum of squares total. So this is asking us why that is. So the first answer is wrong. The second answer is the correct answer. Sum of squares total is based on residuals from the grand mean. Sum of squares error is based on residuals from the group means. Now this is something that we're going to even talk about more today, but pretty soon you're not going to make this mistake again. I don't believe you are. So the sum of squares total is the total amount of variation in the outcome model based on the grand mean, which is the null model, okay, where everybody gets the same prediction. That's the lowest variation we can get without adding an explanatory variable. And then as soon as we add an explanatory variable, we're going to calculate sum of squares error, but that's error around the model, so the predicted. All right, so let's just keep going. And today I noticed I brought a lot of whole everywhere questions, and I'm not going to give you lots of time to think about them. I want you to answer quickly, and let's just get some of our misconceptions out and talk about them as quickly as we can. But the main point I want to make today is that everything you know about group models is going to apply to regression models. There are going to be some adaptations that you have to make, and those are the things that that I want you to focus on. Honestly, this is the real value to the approach we're taking, because most times after you study analysis of variance in statistics and then you do regression, it's like a totally different bunch of stuff you have to learn. It's actually exactly the same as what you've learned in your group model. So if you can learn how to make those connections and incorporate them all into your single sort of mindset or representation, then you're going to get that. And that's what I'd like you to focus on this week, is working on making sure you're working on those connections and asking questions if you don't understand. So in order to do this, I decided to go back to our US states database. And if you recall, what were the rows in this data frame? Does anybody remember? States. Okay. So we had a variable called obese, and I printed out the head of this data frame, and you can see obese has numbers like 28.9, 27.4. So this is the percentage of people in the state that are considered obese. So how many rows in the data frame? Just shout it out. 50 rows. Okay, that's good. How many states in the United States of America? You're not sure about that. 50. Okay. So there's 50 rows. So under smokers, the 24.8, 24.9, that's the percentage of the population that smokes. And then I made a new variable using Entile called smokers 2 group. And I just took the states and I divided them into 2 groups, high smoking and low smoking. Just took the median and divided it into 2 groups. And I also turned smokers 2 group into a factor. So that's something you do need to pay attention to. We'll talk about it a little later. But when you're doing a group model and you're fitting it using LM, which you guys do, you want to make sure it's a factor and not a numerical or interval variable. And there's stuff on that in your book also. So then I went and I just plotted these distributions. And on the left, I plotted the 2 group model. And on the right, I plotted the regression model. And by 2 group model, I just took the the dots and organized them into the low smoker states and the high smoker states. And then on the right, I took the actual percentage of people who smoked, put that on the x-axis, and then the percentage who are obese on the y-axis. And you can look at that and already begin to see some sort of pattern going on there. So here is a poll everywhere question, which is, do these two dots represent the same state? Look at those graphs and see, do those two dots represent the same state? Okay, and try to answer really quickly. Just zip into it. All right. Everybody got an answer? Okay, so let's see what you guys said. Okay, 52% said yes, 31% said no. The correct answer is yes, but that means only half of you saw that that was yes. So how can you tell that these are the same state? Anybody explain that? And by the way, this is exactly the kind of thing, you just need to study graphs and look at them and apply your thinking. So how can you tell they're the same state?
The dots are both on 20, and well, this one's on 20 in the regression model. And before the one you showed us before, you stated that 20 was in the low range. So I assumed that they were the same.
So the low range of what?
Of
Smokers?
yes.
Okay. And how many other people think it's in the low range of smokers? I think it's in the low range of smokers, but it's just barely in the low range. Does anybody have a better explanation of why those two are the same state? Thank you.
It's the lowest, well, if you're talking about like percentage obese, it's the lowest for most of them.
Yeah, that's what I would say. If you look at this as percentage obese, and by the way, each dot on the right side is represented by one dot on the left side. I haven't done anything to change the number of states or anything like that. All I've done is taken and organized them a different way. And so if you look at that dot, it's the absolute lowest percentage obesity of any state. So on both sides, you can see it's the lowest percentage of obesity. And it could have ended up, you know, you can see it's probably in the low smoking group, but it's not the lowest of the smoking. Okay. All right, so if you got that wrong, look at more graphs and just think about them. Okay. Here's another one. Where can you see the smoker 2 groups in this scatter plot? Okay? So I'm just going to start the question so you can see it on your phones. But where can you see the smoker 2 groups in this scatter plot? And remember, it's the same dots organized in a different way. Okay, we're going to go quickly. All right. The right answer is. Okay, there's a lot of variation here. You guys need to look at graphs. By the way, I didn't give you much time. Maybe if you looked at them for longer, you would have seen this. But let's go back and take a quick look. So you guys, the most common was they're the dots on either side of a vertical line at the mean of smokers. That's the correct answer, okay? So if we go back here and imagine a vertical line, I should have drawn this, by the way, right up through the mean of smokers. Where do we see variation in smoking? On the x-axis or the y-axis? Gesture, please, so I can see. Where's the variation in smoking? It's here. So if we're dividing it into 2 groups based on high smoking, low, it's going to be right in the middle of that variation. So it's going to be a vertical line, and the dots on one side, how many dots? going to be 25 dots on one side and 25 dots on the other side, okay? They are dots above and below a horizontal line at the mean of obese. That's the most common incorrect answer. And again, we divided our smoker 2 group based on smoking, not based on obesity. So we divided up based on smoking, but the obesity could be whatever it is. We're not dividing it based on obesity. And so if you look at variation in obesity, which is on the y-axis, you're not going to see the separation between your smoking groups. And it has nothing to do with the regression line, even though I know you just did chapter 8. And good, got some questions. Thanks, Dave. Yes?
If you use the mean, doesn't that not guarantee 25 on each side?
We didn't use the mean. The answer said what? Did I have the wrong answer? Well, hold on. I'll look at that. But we used the median. We used n-tile. And when you use the median, we know it's exactly 25. Did that change what the answer should have been? Really? Good grief. I might have to quit. I'm wrong. That's crazy. Let's see. Oh, yeah, you're right. It should say there the dots above and below, to either side of a vertical line at the median of smokers. On the other hand, there's no other answer that's better than that. That's the closest, because the mean and the median are fairly close. So, but I'm embarrassed, and I will change it. And I will take a lower grade. Okay. All right. So, model predictions. Again, let's look at model predictions under these two kinds of models. So, first of all, what's the model prediction under the empty model? The mean. Everybody got that? And the model prediction under the group model is the group means. And the model prediction under the regression model is going to be determined by the regression line. And we're going to spend some time looking at how that works and how it's related to the mean. So first, let's just make sure everybody's on the same page in terms of how do you get a predicted score from a regression line. So if a state has 15% smokers, what would be the regression model prediction? What would the regression model predict their percent obese would be, okay? So if the state has 15% smokers, what would you predict according to the regression model, the percent obese would be? Thanks for being so quick today. Chuck through a lot. 15. Okay. Let's see what you got. 20%. I think that is the closest. But again, we've got some variation. The most common incorrect answer was 15%. Just for fun, let's think about that. The way you predict off the regression line is smokers is the explanatory variable, obesity is the outcome variable. So just like the group mean is the prediction in the two-group model, the line is the best prediction in the regression model, which means for 15% smokers, you look right above 15%. Yeah, I drew it out. You follow that red line straight up from 15%, and then you go look, where is that on the obesity scale? And it's about 20%. The closest is probably about 20%. So 15% isn't even on the chart. Is anybody willing to ask? Who answered 15%? Willing to ask a little more so we understand what you're thinking? I would appreciate it if you did. No? See, that's gonna hold you up. All right, somebody thinks 15%. There's nothing wrong with that. I just can't figure out what you were thinking. Can anybody else think why someone might answer 15%? Yeah, to this, and explain it. You didn't have to come up with it, but can someone come up with an explanation? I'm having trouble with it. Okay, good. Maybe this is a better approach. Maybe you did answer that. I don't know. No, you don't have to say.
I won't say. Maybe it's because the x-axis and the y-axis have different intervals, and so maybe someone was using the same intervals as the x-axis to determine the y-axis interval. I don't know.
So maybe someone wasn't actually reading the
Yeah.
units on the obesity axis. That's possible. That's possible. But anyway, that's the basic idea, is that with the regression model, we do that best fitting regression line, and that's the line we're going to use as our prediction. What's different? Well, there's some things that are really the same about this in the mean. For example, if you look at 15% on smokers, are there any dots at 15%? There's one that's kind of close up above there, see? And you could say, well, maybe that's the closest dot, so maybe we should predict that, 22%. But that's not the way the regression model works. Just like in the average as the model, in the mean models of groups, sometimes you predict the mean and there's no scores near the mean. But that's still going to be your best prediction, okay? And the same thing works with the regression model. So here's perhaps the most confusing thing about the regression model and the two-group model, and that is if you write the model specification in GLM notation, and I would like you all to be able to write this. In fact, write these in your notebook. And now that the projector is nice and bright, you might notice that they're exactly the same. Okay? And that could be a good thing, and that could be a bad thing. The good news is you don't have to learn some totally new thing. The bad news is they are different, and you need to interpret them differently. And if there's one thing that I want you to remember, it's that to understand what these symbols mean in the GLM notation, you have to interpret each one in context. Now, what does that mean? It means that y sub I, by the way, just says y sub I. You may notice, we call every outcome variable y sub I, whether we're measuring obesity in states or how many inches tall you are in OkCupid, we still call it y sub I. And so this problem that we're presenting with regression and the two-group model is the same kind of thing. We're using the same symbols, but we're interpreting them differently. Y sub I is the outcome variable, so whatever it is going to be the same. In this case, the two y sub i's are the same across the two models. What's the y sub I? Anybody? Louder. Obese. Gesture, obese. Percentage obese. Okay? All right. So y sub I is the same. What is x sub I? What is x sub I in these two models? What is x sub I in the group model, the two-group model? Who can answer? Think about that. So what we're doing is we're mapping these symbols on to each different situation.
It's categorical, low or high.
Okay, it's low or high percentage smoking, okay? And what is x sub I in the regression model? Anybody? Just talk about it. What do you got?
Every person's height.
It's no height is involved. Remember, this is the model where we're looking at percent obese, and the explanatory variable is percent smokers. Percent smokers. Okay, I think that's what you meant. I think I confused you. But if we did have height and we were using it, we'd be using the same symbol. But the reason this is important is because you need to look at, just like in your, there's a few things you have to understand. First of all, you have to know what the rows are in your data frame. So your outcome variable is a characteristic of states. It's not a characteristic of people. It's a characteristic of states, the percentage who are obese. And it's the same outcome variable in both cases. X sub I is going to be coded differently if it's a categorical variable than if it's a continuous quantitative variable. So, and that's why we went through all that stuff in the book about how we're actually coding X sub I. And a lot of people had questions about interpretation 1 and interpretation 2, and some people said I should cut that out, and we might because we're only using interpretation 2. But it's very important to know that X sub I is going to be coded by R as 0 or 1 in this case, okay? We know that because it's a categorical variable, and there's only 2 groups, and we also know that the B sub 0 is going to be the mean of one group, and the B sub 1 is going to be the increment that we add to the second group. Remember that? Okay? So when you're talking about regression, we have to take that idea of increment, and we have to think, what would that mean in the context of a quantitative predictor variable or explanatory variable? So if B sub 1 is the increment between the 2 groups in the 2-group model, B sub 1 is the increment for each unit of X sub I in the regression model, which is percent smokers. So it's going to be some parameter we're estimating where we say, whatever it is, and we'll see in just a second, but it's some number multiplied by the percentage of smokers. And then we're going to use that to adjust up from B sub 0, which in the regression model is the y-intercept. So the key is, whenever you're fitting these models, think about the variables, think about how they're measured, and from there, think about what kind of model you're fitting and how to interpret these parameters. What about E sub I? Is that the same, or is that different in these models? It's not. What's E sub I? What's E sub I in the group model? Yeah.
It's the error of each state to the group models.
Okay. E sub I in the group model is based on the residual actually from the predicted group mean to the individual score. And error in the regression model, we're going to look at it in just a second, but it's really the same thing. It's how far the individual score is from the predicted score. It's just that in the regression model, we're using a different predictor, which is going to be the regression one. All right. So fitting the 2-group model and fitting the regression model, guess what? It's exactly the same R code. So that's the good news and the bad news. The good news is you guys already know how to do this. LM. Okay, you just say LM for regression, obese, squiggly thing, or tilde, smokers, data equals US states, and that's going to fit your linear regression model. The exact same format is going to be used for the 2-group model, but instead of putting in smokers, which is the quantitative variable, we're going to put in smokers 2-group, which is going to be 0 or 1. Are you a high smoker or a low smoker? And if you look at these, you can see that when we fit these models, the output in both cases is going to say intercept. And in the 2-group model, it says smokers 2-group high, 3.608. And in the regression model, the intercept is 10.9, and smokers increment is 0.648. So let's look a little more detailed at these things right now and ask some questions. And I don't think these are told everywhere, but these are questions that are worth thinking about. Okay, so why is the y-intercept so much higher for the 2-group model than it is for the regression model? Look at that and see if you can answer. And think about y-intercept. Who can give me a definition of y-intercept? What's the best way of thinking about y-intercept? Y-intercept? Yes.
Isn't that when the x-intercept is at 0, the y-intercept is the point that is on the y-axis?
Yeah, when x equals 0, where is y? That's the y-intercept. That's where it's going to cross the y-axis when x equals 0. Okay, so why is the intercept so much higher in the two-group model? Two-group model has an intercept of 22.75, and the regression model has an intercept of 10.93. Who can come up with an answer? Yeah.
In the two-group model, the y-intercept is the empty model, or the mean? Right?
No.
No.
But it's not. And let's think about that for a second. You mean the mean of the whole sample?
Yeah, the grand.
Okay, so go look at the equation here. If x is 0,
Oh, it's of 1.
I know why you're saying that. You're saying if x is 0, then b sub 1 gets zeroed out, and you're left with b sub 0, and you're thinking, oh, that's the grand mean. But that's the grand mean in the empty model. It's not the grand mean in the two-group model. Okay? In the two-group model, what is B0?
Group 1.
It's the mean of group 1. So if x is 0, 22.75 is going to be the mean of group 1. And by the way, when I'm doing these analyses, I don't trust all this stuff to say, you know what, I'm going to check that. So what do? I do a FAVStats. You know, I do a FAVStats of obese by smoker 2 group. And I look to see if the average for one of the groups is 22.75. And guess what? It is, because I actually did that. And that's the kind of thing I want you to be thinking of doing, is just check it multiple ways. But do people see why that should be the mean of group 1? And what about the y-intercept in the regression model? Why is that so low? What is the y-intercept in the regression model? Who can explain that? Thank you for getting that wrong, because that gave us a chance to figure out what would be a misconception people would have. Yes?
It's when the smoker's value is 0, what their obesity is.
Okay, so when what is 0?
The smoking value.
And what's the smoking
The
value?
x.
And what is that? Remember the exact measure? It's
In
percent
yeah.
of people
Percent
in
of people
a state
that smoke.
that
in
smoke
state.
is 0. Okay, so here's a problem with regression y-intercepts, is often you get to, you draw the regression line, and guess what? Do you think there's any states where 0% of people smoke? No, there's not. So in a sense, the y-intercept is very hard to interpret in a regression model, because often there's no such thing as that value of 0. So that's something to keep in mind. It's not even appearing on the graph here, right? Because remember, smokers only goes down to 15%. If you keep going over to here, like 10%, 5%, 0%, you're way over here, and 16 down, and the 10 is going to be like way off here in space. Okay? It's theoretical. It tells you what shape to make the line, but it doesn't really give you something interpretable. And there are things people do to make those things more interpretable, which you can learn later if you do more advanced statistics, like recentering the smokers, for example, so that the intercept actually makes sense. But for now, that's the difference between these intercepts. So you have to look at the variable you're measuring. If it's a categorical variable, then it's going to be one of the group means as the intercept. And that's going to be very interpretable, because that is going to be the mean for that group. And smokers 2 group high, that's going to be the increment. All right, here's another quick question. All right, looking at the LM output, can you tell if X is categorical or quantitative? All right, this is something that actually could have been useful for one of the quiz items. But if you just look at the LM output for the 2-group model, can you see what it says? It says smokers 2 group high. Okay, that's how you can tell it's a categorical variable, because it's terrible formatting, honestly. Not very readable. I don't know why they don't make that better. I think they think it's cool to not have it be better, honestly. But what they're taking is the name of the variable, smokers 2 group, and then they're just adding on the name of the sub of the level of that variable, high. And as you see that, what that's telling you is that x sub I, what is that telling you about the coding of x sub I? Who thinks they can figure that out just by looking at this? So how is x sub I coded in the 2-group model just based on the element output? You see that? What do you see? Say again?
Would it be the a 1 if it was high?
Yes. Why?
Because 0 is for low.
Because 0 is for low. And how can you tell that?
It says high there. And
Okay, and because you want to be multiplying by 1, okay, so if x sub I is 1, then that increment, which we've estimated that's d sub 1, is going to be multiplied by 1, which is going to put it in that higher group. Great answer. Good. Why do you need to check to make sure x in the 2-group model is a factor in R? Can you guys remember this? Did you have another question, by the way?
Yeah.
Please.
Where exactly is the 1 coming from? Just by looking at.
Okay, where is the 1 coming from? Okay, that's a great question. So first of all, the way these variables are coded in R is it takes every level of a variable, everything that defines a group, and it only gives it one of 2 codes, 0 or 1. It's called dummy variable coding. So, and the way that works is, so x sub I is either going to be a 0 or a 1. So that's the first thing. And so if it's, and so it's going to be 0 if they're in one group and 1 if they're in the other group. The fact that the increment is labeled as smokers 2 group high means that's going to be the group that's identified if it's 1, because then you're going to multiply that increment times 1 in order to get the group mean for that higher group. Okay? So, does that make sense?
Yeah, it was just because I was confused. You said just by looking at it.
Well,
So I thought we had to look at the numbers.
well, you can look at the numbers, but mainly I want you to look at where it says smokers 2 group high, because that indicates the variable is called smokers 2 group, but high means it's the high group. And the high group is what's getting that increment. It's a kicker. So one group, the mean is 22, but if you're in the high group, you get an extra 3.6. And that's if you're in the high group, which means high group must be coded as 1 on x sub I. Because if it's 0, you don't get that kicker. Okay? All right. Why do you have to make sure x in the 2-group model is a factor? This is actually a little bit of a problem if you do it wrong. You got an answer? All right. I appreciate it.
So wouldn't like R think that it's a quantitative variable instead of a categorical variable, and that will give you like accidental regression?
Okay, that's exactly right. If you put in numbers to code your groups, which we do all the time, let's say you say, oh, I'm going to make 1 equal to the low smoking group and 2 equal to the high smoking group. If you don't tell R that those are categories, it's going to assume it's numbers. And what it's going to do, it's going to take those 2 numbers, 1 and 2, like in the left-hand figure here, and it's going to fit a regression line across those. And guess what it's going to estimate the y-intercept to be? 20. And that would be wrong in the 2-group model, because we know the mean of that one group is 22.75. So that's another reason I check these things, is because I look at my mean and I say, that should be 22.75. If it comes back and says 20 or 19.8 or something like that, I'm going to say, oh, I must not have made that a factor. So R doesn't know it's a categorical variable. So it's just about explaining things to R that R would understand if it were an intelligent human being. But it's just a computer program. Yeah. Yes.
On the graph on the last slide, it just seemed like the y-intercept was off. I was wondering if it's supposed to be congruent with numbers here in the two-group model.
Yeah, that was just artist's rendition of what could happen. It's not actually true. But actually, I don't know exactly what that y-intercept would be, but do you think it would be way off?
Well, I'm just wondering why you have a line going through the two.
Oh, I drew that line because if R thought that this was a quantitative variable, it would fit a regression line. And it would tell you the y-intercept and the slope, even though it wouldn't really make much sense. Because if I coded this as 1 and 2, and I only had two groups, what does it mean to say what is y when x is 0? Because there is no 0. It's just extrapolating out and saying we're going to fit a straight line. So it's just a matter of making sure that R knows it's a categorical predictor or explanatory variable and not a quantitative one. Does it matter how you code x in the two models? I mean, this is kind of interesting. The truth is, if it's a categorical variable, R doesn't care how you code it. It's going to code it 0 and 1. As long as there's two levels of the category, it's going to code 1, 0, and 1, 1. Okay? For every level, it's going to say, is it that level? Either no or yes, 0 or 1. So you could code, if you coded smokers as low smoking states, I'm going to code 1. High smoking states, I'm going to code 1 million. And then you made that a factor. R would not have a problem with that. It would give you exactly the right estimates. Because it would say, oh, it's a factor. It's categorical. Those numbers don't mean anything. But if you tell R that the numbers mean something by using a numerical variable, then R is going to say, oh, we're going to fit a line to that. We're going to look at the slope of that line and the y-intercept. All right, let's talk about error in both the two-group model and the regression model. And we haven't looked at any formulas recently, but let's go back to our sum of squares formula. And let's look at this and see if you can answer this polar everywhere question. What is this the formula for? Sum of squares total, model, or error? What is this the formula for? And write this formula in your notebook. Everybody remember that we read this as y sub I minus y hat. So the key is looking at what is y hat. It's a clue to help you. So this is a sum of squares. You can see that because of the structure of this formula. It's the sum of each data point, y sub I, subtracted from y hat, squared, and then summed up across all data points. All right, let's see what you guys got. Quick answer. Whoops, my little beach ball. All right. All right. This is something you need to think about. We have a lot of disagreement about what sum of squares this is. All right. Who thinks this is sum of squares total? 40% of you. Who would like to know the right answer? Finally got a response. Okay, the right answer is this is the sum of squares error. So let's think about why that is. Okay? Remember, what is y hat? Predicted. Y hat is predicted. And what do we use? What predicts y hat? the model, okay? So we have two models we're talking about right now. One is the two-group model, and y hat is going to be either the mean of group 1 or the mean of group 2. And the other is the regression model, and y hat is going to be the point on the regression line perpendicular above the level on the explanatory variable. And those are the predicted scores. So when you take the sum of squares around the predicted scores, that's error around the model. That's not from the grand mean. The sum of squares total would be from the grand mean. Sum of squares total comes from the empty model. Okay? So anybody who said sum of squares total, and there are a few of you, like almost half of you, this is not sum of squares total. This is the squared deviation from the model prediction. So just think about it in terms of a two-group model. We have group 1 and group 2. The model prediction in one group is going to be this level, say it's 20. The other group is going to be 25. And the null model, or the empty model, is going to take the deviation from the grand mean, which is going to be the mean of all the points. And that's going to tell us how much total variation we have. But taking the sum of squares from the predicted is going to show us how much sum of squares error there is. Yes?
What if you're using the empty model and your best prediction is the grand mean? Would that not be the sum of squares total, which is the exact same thing as sum of squares error?
If your model is the empty model, and that is your model, then your y hat is the grand mean.
Which
Okay?
would be sum of squares total and error at the same time, if it's the empty model you're modeling, correct?
Yeah.
Okay,
But-
I just want to clear that up if that's confusing.
Yeah, we don't. Yeah, that's true. But if we're using the empty model, we're really just using it as a comparison to the other models. And we're trying to find out how much our two-group model and our regression model are accounting for. And the error we get by subtracting each score from its predicted score and squaring them and summing them is going to tell us how much error there is left after we've taken our model out. Okay? Yes? Yeah. That's okay. I got the mic.
So to clarify, in order to make that equation SS total, would you just switch out y hat for y bar, and then that would be representative of it?
Yeah, if you're going to talk about SS total, you would use y bar. You wouldn't use y hat. We don't usually think of y hat when we're talking about the empty model, but I can see why you would, because if that is your only model, then your only prediction is the mean. Yeah.
So how would you, like, what would be the equation for SS model?
Ah, okay. What would be the equation for SS model? All right, we're going to talk about that in just a second. I brought some pictures to help explain that. But that's a great question. But the short answer to that is there's a couple of different ways to find SS model. The easiest way to find SS model, I'm only going to tell you one now. I'll tell you one in a little bit. The easiest way to find SS model is to take SS total and subtract SS error, and the difference is going to be SS model. Because remember, data equals model plus error. So sum of squares total equals sum of squares model plus sum of squares error. So if you know what sum of squares error is, which is easy, that's just the deviations, the squared deviations from the model prediction, and you know what sum of squares total is, that's just the sum of squares for the outcome variable around its grand mean, then you subtract those two and you get sum of squares model. And there's another way to think of it too. All right, another quick poll everywhere question. Which of these can never be used as a parameter estimate? So now I'm asking you to think again about the sample distribution and the population distribution, the data generating process. So what's the parameter about? It's not coming up? All right. That would explain why no one answered. Okay. So which of these could never be used as a parameter estimate? I know I'm asking you to think a lot today. Does your head hurt? A little bit? Okay. All right, let's just see what we got here. Which one would not be a parameter estimate? Okay, a lot of variation. The correct answer to this, though, is sum of squares. So think about this for just a second. Each of these other things, variance, standard deviation, mean, we know that we can talk about the mean of our sample. We've called that y bar. And the mean of the population, we call it mu. Those are two different ones. We use our sample mean to estimate what the population mean is. And we do that with the standard deviation, and we do it with the variance. We can't do that with sum of squares. Why? Can anybody give us a quick explanation for why sum of squares can't be used as a parameter estimate?
It's because sum of squares has to do with the data set that we're dealing with, like the sample that we're working with, not with the entire population.
Yeah, because sum of squares has to be calculated. And every time you have more in your sample, your sum of squares grows. So the idea of sum of squares of the population, it means you would know every single data point in the population, and you would know its square deviation from the model prediction, and it just doesn't make sense. So we would never estimate that. To estimate that, we'd have to know a lot of things we don't know. So I just want you to keep remembering what we're talking about between estimates and parameters. All right. Sorry to ask you so many questions, but it's not like you're getting them all right or anything. So, all right. This gets back to your question. All right. Which distance, and this is in the two-group model, is used to calculate sum of squares total? Okay. So we've got a group mean, y bar sub 1. We've got the grand mean, which is y bar. And just think about the blue dot for now. I mean, you can think about the yellow dot too, but just think about the blue one. So which of these distances, A, B, C, or none of these, is used to calculate sum of squares total? Did the question get opened up? Good. I kind of think you guys are going to get this one right, which is going to make me feel really good, based on our discussion today. All right, let's see how you're doing. All right, just a few more people, and here we go. Excellent. C, that's the sum of squares total. It's the distance from the point to the grand mean, okay? And that's the residual. That's the basis on which we calculate sum of squares total. All right, great. That's really good. Which distance is used to calculate sum of squares model? And this is actually your question from before. And this is the answer to your question from before. So which of those distances, A, B, or C, would you use to calculate sum of squares model? Think about this. I really think you're all going to get this one right too. As a little hint, think about what are the three kinds of sum of squares we're talking about. Total, model, and error. That's it. There's no other sum of squares. All right. Let's see what you guys did. Go ahead and answer. Oh, what?
Fight it out.
Shoot. You know what? Half and half. Half said A, half said B. Actually, fight it out is a great idea. Talk for 2 minutes with the person next to you and see if you can change each other's mind. out? All right. I just opened up another question. You can change your mind if you want to. Which of these is used to calculate sum of squares model? A, B, or C? You can answer again. It's locked. I'm unable to act that quickly. I'm not good at questions on the fly. You know what? We don't have a lot of time. Forget that. How many people, I'm just curious, how many people changed your answer? Raise your hand. Oh, it's not that many. Okay. All right, let's think about this. Remember I showed you that equation? This one. I can't figure out how to get it done in a few minutes. All right, remember this equation? The sum of all y sub I minus y hat? That was the sum of squares of what? Total, model, or error? That was error. Okay, so let's go back to this picture. And the distance A, which is from the blue dot to y hat, which is labeled y bar 1. So that makes this a little more complicated. That's the mean of one group. That's going to be the sum of squares error around the model prediction, because that's your model prediction for the two-group model. C is the sum of squares total. B is that difference between those two. So B is the direct way to calculate sum of squares model, is you take the distance from the model prediction to the grand mean. And if you do that for every row in the data frame, you'll get, and you square that distance, and you sum it all up, you're going to get the sum of squares model. All right. Wait 1 second. Can you wait 1 second? All right. This is what I want you to think about between now and Thursday. Why does it make sense to think of sum of squares model as reduction? Think about that. All right, we'll see you Thursday.